Assalamu alaikum, dear students. I am Tahir Yusuf from JK College. Today I am going to discuss about the topic Gauss's law, which is for class second year, and this topic is taken from the chapter 11 electrostatics. So, from previous lecture, we described the flux, which is electric flux, for an arbitrary shape, and this flux is for the charge which is enclosed in a closed surface, like this is any closed surface, and we place a point charge q inside the closed surface, and we know that the electric field lines are passing outward direction. These are E. So for this we derive an expression 1 over epsilon naught times of total charge enclosed in it. This is the total flux of any charge which is enclosed in a surface is equal to 1 over epsilon naught times of the total charge enclosed in it. So this is the flux for any charge which is enclosed in a closed surface. This is for arbitrary. Now we are going to discuss the Gauss's law. Gauss is a mathematician and scientist. He derived many theories, like he contributed many fields including number theory, statistic analysis, differential geometry, geophysics, electrostatics, astronomy, and optics. He contributed in all these fields. Before this, we can find electric field by using Coulomb's law, but this is an alternative method to calculate the electric field for a given charge which is distributed over a surface, and this law is called Gauss's law. So for Gauss's law, we have a closed surface and the charge distributed inside an infinite, means we have, this is q1 positive charge, this is q2, we have n number of charges inside this closed surface. Let's suppose this is qn, this is the nth charge. We have n number of charges, like from here this is positive charge q3 and this is qn. N is any number. So for this we calculate for flux of charge qn. We get a formula from the above equation, which is flux 1, which is equal to 1 over epsilon naught times for charge q1. For q2, we can write equation 1 over epsilon naught times charge q2, and for n number of charge the flux is phi n, and that is equal to 1 over epsilon naught times q, and qn is any number. So the total flux for this closed surface is the sum of, this is a total flux, and this is equal to the sum of all the individual flux, that is phi 1, phi 2 plus so on, and that is the nth flux. When we put the values for these individual flux, we put values from this equation 1, 2 and 3, and we put in the general equation. So we get 1 over epsilon naught times q1 plus 1 over epsilon naught times Q2 and 1 over epsilon naught times of Qn. So you see this 1 over epsilon naught times, this is common in each term, so we common this value 1 over epsilon naught and add up all the charges. So this makes the sum of all the charges which is enclosed in a closed surface. So the general flux or the total flux for all the charges is, the flux is 1 over epsilon naught time, and we represent this by a capital Q. This Q is the total charge which is enclosed in it, so we can write this. So this is the general formula by the definition of Gauss's law. So this is the Gauss's law, and Gauss's law states that the total flux of a charge which is enclosed in a closed surface is 1 over epsilon naught times of the total charge enclosed in it. In previous topic we get the small patches of areas, and for that we calculate this value, and now we prove that the flux is not depends on the shape or geometry of the sphere or closed surface. This is not only for a sphere, this is for arbitrary shape or any other shape like triangle or circle, rectangle. For any shape we use this Gauss's law. So by definition of Gauss's law, the flux, the total flux is equal to 1 over epsilon naught times of the total charge enclosed in that surface. Start. Now students, I am proceeding towards another topic, which is the applications of Gauss's law. Now we are going to study application of the Gauss's law. Gauss's law provides a convenient method to calculate E. E is the electric field intensity. In the case of sufficient symmetrical charges which is distributed over any surface, so for that we are first calculate, and now for first finding the electric intensity for a charge, for a hollow charge sphere. I am going to draw the hollow charge sphere. The charges is distributed over the surface of that sphere. In your book, this topic is named by the location of excess charge on a conductor, or in previous book the question may given in your paper, that is find electric intensity for a hollow charge sphere. So now first of all, for finding this E, we have a point, this is a point P, and we are going to find electric intensity for that point. So first we make a Gaussian surface. This is compulsory for Gauss's law. This is the Gaussian surface. This surface contains that point for which we can calculate E. So the Gaussian surface is contain the point P. So you know that positive point charges, the electric field for the positive point charge is radially outward. So you can see no field lines cross that Gaussian surface. This is an interior surface inside the sphere. So no line cross this Gaussian surface. So by definition, we can say inside a sphere E is equal to 0. So how? By definition of Gauss's law, flux is equal to 1 over epsilon r times of the total charge. Let the charge is q. This is definition 1. And by definition of electric field, electric flux, sorry, by definition of electric flux is E dot A. It means for maximum flux, this is EA. So this is equation 2. When we compare equation 1 and 2, we get EA, that is equal to 1 over epsilon r times charge q. So from this equation, let me say that this is equation A, this is a general equation. So from this, no charge will be there on Gaussian surface. So here inside, I say inside a sphere there is no charge. It's mean the flux will be 0. When flux will be 0, it's mean EA is also 0. So from this we can not say that A, which is the area, A is not equal to 0, but it's mean the flux will be 0 because area is placing, we have some surface area of that sphere. So the flux, it's mean the flux is not passing through that Gaussian surface. So we can calculate for a hollow charge sphere, it means it's a hollow from inside, no charge will be there. So for that we conclude that for hollow charge sphere there will be no electric field intensity for that surface. This is 0 because area is no, we can say area is here. So area is not equal to 0. Flux is 0 due to no charge placed inside the surface. So this equation A becomes E is equal to 0. So from the definition of Gauss's law and electric flux, these two definitions, we can use these two definitions and we find the flux is 0 inside a hollow charged sphere. So for any numerical problem or the question which is given in ETA papers, for when they say find the electric flux inside or electric intensity inside a hollow charged sphere. So there will be no intensity because no field lines passing through that surface. We can say that by definition of electric flux, we defined electric flux that time the number of field lines passing through some certain element of area. If some lines passing that area, so for that we can say the flux will be maximum. But here there is no field lines passing through that point P. So for this we can say that flux inside a hollow charged sphere is 0.
Start, sir.
Now students, I am proceeding towards another application of Gauss's law. We can find electric intensity due to infinite sheet of charges. So here we have a sheet containing n number of positive charges with charge density. This is a new term for you students. We denoted this charge density by sigma. It's called sigma. So you know that the mass density, or the simple we can say density, the formula for density is equal to mass divided by volume. So when we divided mass divided by its volume, so we get density, which is called mass density. So here we have a charge density. It's mean the charge occupy here some space. It's mean when a charge divided by its let me say its area, because it's two-dimensional. So this is called the charge density. So let me start again. Consider an infinite sheet of charges with surface charge density sigma. Let's produce a point. Let me say this is a point P. So we can find electric intensity at that point P, which is on the surface of a Gaussian cylindrical surface. We can find electric intensity for that infinite sheet of charges. So we can make a Gaussian surface. This is a Gaussian surface which contain the point P. Let me say its point P can be here. So this is the surface of that point P, cylindrical P, and this is the P dash. So P at the point at a distance R from the sheet. So consider the Gaussian surface in the form of a cylinder of cross-sectional area is capital A. So capital A is the cross-sectional area of that cylinder. A perpendicular sheet of the charges, and the direction of E is perpendicular to the face. So we can say that the electric field, this is the parallel of that point. So that on two surfaces, which is one is P1 for the face P1 and for face P dash. These are parallel. Electric field lines are parallel to each other. So this surface, let me draw the cylindrical surface. I can explain more here. This cylindrical surface has three faces. One, this is one, this is two, and the one is curved surface. This is surface 3. So we can write three fluxes for this cylindrical sphere. This is the Gaussian surface we can place in that sheet for finding electric intensity. So for faces 1 and 2, for this is flux 1 for that surface, for that surface this is flux 2, and for this is flux 3. So we can see the phi 1, that is the P, that is P dash, and let me say this is Q. So for P, you can see that these two are parallel each other. It's mean the area is perpendicular to the vector area. So for this we can study earlier, for these two surfaces, for P and P dash, flux will be maximum. So we can write, by definition of flux, we can write that is equal to EA. I can write in general form. EA and EA both are added makes 2EA. This is the flux for surfaces P and P dash. For curved surface, now I am going to write flux for this curved surface. So this area is parallel to the field lines E. So for that surface there is no flux or minimum flux. This is the definition of maximum flux. And for surface, let me say this is a face Q. For Q there will be no flux. So the total flux for that Gaussian surface is equal to 2 EA. Now, by definition of Gauss's law, this is from definition of electric flux. Now we can write flux by definition of Gauss's law, which is equal to 1 over epsilon naught times of Q. This is equation 2. So compare equation 1 and equation 2. We get 2EA, that is equal to 1 over epsilon naught times of total charge. So by charge density, we can say charge density is equal to Q divided by A. So from here we can write the total charge is equal to sigma A is equal to the charge density into area. So put these value here and we get 2EA, which is equal to 1 over epsilon naught times sigma A. So by mathematical rule, the area is cancelled by that area and we get the electric intensity, which is equal to this 2 goes to it there, which is equal to 2 epsilon naught times of sigma. And when it's a vector form, so we can place R dash there. It's mean R is the unit vector. We can say R is the unit vector. So this is the expression for the electric intensity due to an infinite sheet of charges. This sheet may be like this whiteboard. This whiteboard contain n number of charges. So he can find electric intensity, which is for infinite sheet of charges 1 over 2 epsilon naught into sigma, which is the charge density. So charge density is new for you, so we can explain. So this is the electric intensity. This is a more important topic, and in exam point of view, the question may be given that find electric intensity. You just add find electric intensity due to infinite sheet of charge. So this is the long question in your book.
Start.
Now students, I am proceeding towards another application of Gauss's law. This application is find electric intensity between two oppositely charged parallel plates. So here we have two plates. One is plate A and the other is plate B. This is two oppositely charged plates. Plate A contains positive point charges and plate B contains negative point charges. Students, you know that the electric field lines originate from positive and ends on a negative charge. So these green lines are the electric field. It means this is E, which is from positive to negative direction. Here we have a point P and we find electric intensity at that point. So for that we get an rectangular Gaussian surface. This is a Gaussian surface which is necessary for the calculation of electric intensity, and we can apply Gauss's law only on that surface. So P is the point which is inside a Gaussian surface, and that Gaussian surface is in a rectangular form. So now we can calculate the flux by definition of electric flux. By definition of flux, so we flux for surface AB we can find. Now first I can write the all fluxes for flux BC and for flux CD and for flux dA. This is the flux AB, which is for this area. This is the flux of the surface AB. Now, by definition of flux, when area is parallel to the magnetic field lines, which is E, so there will be no flux. So you can see from the diagram, the face AB, this is, and from face CD or AC, these two surfaces or areas are parallel to the magnetic field line. So for AB and CD, the flux is 0. This is the by definition of the electric flux. Now we can write the flux for the face BC. So you can say this is the vector area. Now by definition of flux, vector area and E both are in parallel. So for this, flux will be maximum, which is EA. Now I am going to write the flux for the surface this. So you can see this surface is out from that point charges, and these lines are radially towards negative, not in that direction. It's mean no field lines cross this surface AD. When no electric field lines cross any surface, its mean flux will be 0. So for these three surfaces, the flux is equal to 0. Only the lower surface, which is perpendicular on electric field lines, this may give a flux which is equal to EA. So this is the by definition of flux. We can get the flux for BC, that is equal to EA. Now I am going to discuss flux by definition of Gauss's law. We can say that is equal to 1 over epsilon naught times of total charge enclosed. So from previous topic, we get charge density, which is equal to Q divided by A. So from here, Q is equal to sigma A. So compare equation 1 and 2, we get EA is equal to 1 over epsilon naught times, so we can write the value of Q here. This is sigma A. So these two are fluxes, so we compare or equal equation 1 to equation 2. This is flux and this is also flux. Or you can put the value of flux from equation 2 in equation 1. Both are right. So this is the general formula. So let me cancel the area and we get the electric intensity for opposite charge plate, which is equal to 1 over epsilon naught times into sigma, and R is the unit vector. So this is the formula for electric field between two oppositely charged parallel plates. So this formula is used in your next topic, which is for capacitors. So this is for the capacitors. So remember this formula. We find two values. For one is E for infinite sheet of charges, which is equal to 2 epsilon naught times into sigma R. So here only 2 is extra. So these are the two derivation, important derivation. So these are used in MCQs also. The one option is given this, find the via, or the MCQ will be what is the electric intensity between oppositely, for oppositely charged parallel plates. So the right answer is this, and the MCQs for infinite sheet of charges, the answer is this is right. So students, you study or watch these videos and subscribe our channel, YouTube channel, so you get the updated videos of class 12. Thank you students, be safe.